Hello everyone, I am Dr. Manika Gupta. I am an assistant professor at Department of Geology, University of Delhi. Today in this module, we would be discussing about classification techniques of digital images. So here you will be understanding what is the requirement and need of classifying an image, what are the various approaches that can be applied for classifying an image, and what are the various methods and what is the need and requirement of digital image classification. As an introduction, you can imagine an image from a satellite data is in itself only digital numbers. So we need to classify this information in a manner that is useful to the end users. That is the basic requirement of classifying an image. If you will look at any of the satellite images, it's actually composed of multiple bands in the EM spectrum. So all the bands together form one image, but that only gives us a spectral information. So converting this spectral information into some land use, land cover information or particular information classes implies we are classifying an image. Now what are information classes? Information classes are basically a categorical class. A categorical class like whether that pixel represents a water area or an urban area or a forested area. So basis on the spectral curve or the spectrum of that pixel, we can provide an information what the pixel is going to represent. So if you will look at the given figure, the first figure represents a false color composite. I am sure you must be knowing what's a false color composite. Just to revise it up, this is a composition of 3 bands of the satellite data. So here we have taken band 4, band 3 and band 2 of a Landsat data. So here the vegetation is actually red. But however, if you do not know how to interpret the satellite data by itself, you won't know what this red color is representing and what the blue color is here representing. So we need to classify this image in a manner that we are able to get a land use and land cover map, which is shown in the second figure. So we are getting an information from the first map or the satellite data, and we are able to classify it into density urban, agricultural land, forest and water. So this data is more useful to the end users who need to assess the land use land cover map. Similarly, this same figure can be used or analyzed for other purposes, maybe for water resource management, agricultural purposes, land use change detection, etc. So this is your first image which needs to be classified, and this is the classified image. Now what is the basic assumption we have here to classify an image? A basic assumption here is that if it's a water body or an agricultural land or any other information class, the spectral signature of each class is different. What do we imply by spectral signature? Spectral signature is, if you look here, if this represents one of the bands, band 1, or the NI in the red region, band R, and here we have NIR. So a vegetation would have higher reflectance in NIR and low reflectance in band R. So a point might be somewhere here. However, if it's a water area, then you might have less of reflectance in both of these bands, and you might have water pixel here or even here. So if you would look at the cluster of the pixels, the water pixels might be concentrated at this place, and your agricultural or the vegetation pixels might get concentrated at this location. So you can see there is a difference in reflectance and absorbance in the bands R, that is red region, in the NIR region for both kind of categories. So when we are analyzing our data, these kind of things happen for each of the class. That is, maybe it's urban class we need to identify or a soil class, whatever is your requirement. So this is your basic identification or the spectral signature, which changes on the basis of which class you are interested in. Once you know this, then you move forward. Now if you would look at the band resolution, now the radiometric resolution of the data and the spatial resolution also varies. In your origin, what do I mean by these two resolutions? First of all, if you have a raster data, you will notice that the band data is in the form of equal sized cells. So if this is your area and you have some kind of vegetation in this pixel, you don't know exactly whether it's extending to this pixel or not. So this resolution is known as your spatial resolution, that is a pixel size which can be recognized by the satellite. So if you have two distinct trees in this zone, or if you say in this zone you have two distinct trees, you might not get that spatial identification of these two trees separately. However, you will have a reflectance, a complete reflectance for the vegetation here. So you will have high NIR, but you won't know whether there are two trees or a single tree. That is why you are requiring a classification. If you have a very high resolution imagery like you would see on Google Earth sometimes, or like a spot data which has a very high resolution, you might even able to identify these two trees separately, and you might not need to classify an image. But because usually the image resolution or the spatial resolution is coarser, that's the reason you need to classify the image and tell the user that this area represents vegetation. You cannot tell by this image how many trees are present there, but approximately this zone is representing vegetation. That is your first thing. What is another resolution which comes into play? That is your radiometric resolution. What is your radiometric resolution? It implies the capacity of a sensor and the storage capacity of the sensor, that whether the image is 8-bit image or a 4-bit image or a 2-bit image. What happens in 2-bit image? Now, this is one way when you see the colors. If you look at the original band, suppose an NIR band, this is again your raster cells here, and you will notice some numbers if you look at the original cells. So this might be 255, this may be 0, and any number. So if it's a 8-bit image, these numbers will vary from 0 to 255 because it's a binary digit. If it's a 2-bit image, the numbers will vary only from 0 to 3. So these numbers, on the basis of these numbers, we provide a variation in color from white to black. So here if you will see, if you have a 255, that's the highest number and its highest reflection, that would be in white, and 0 would be black. So in 8-bit image you will have a variation between 256 colors, while here you will have a variation of only 4 colors. So you can imagine a color variation of 256 and 4. Obviously a 256 color image would have a better variation, so your radiometric resolution increases. So on the basis of this, we usually utilize the Landsat data, in which if you will notice, Landsat 7 has a 30-meter spatial resolution and Landsat 7 has 8-bit image resolution. Further, Landsat 8 has increased it to 16-bit resolution. So whichever is important, whatever is required, you can decide how do you want to use, which image you want to use. On the basis of this, we classify our image. Now, what are the various techniques we can utilize for classifying an image? So there are basically 3 categories which tell us that these are the methods which should be utilized for classifying an image. So the first method is your visual interpretation, second is your digital image classification, and third is the hybrid process. Manual interpretation, as you can understand, that is a visual interpretation. Now what happens in visual interpretation? Basically we create a false composite, as I had shown you in a previous figure. So you create a false composite, you give the colors to an image, and on the basis of the knowledge that which category or the information class have which kind of reflection and what kind of a color it gives, you will know that what class it is. So that's kind of totally on the expertise of the person who is classifying an image. So as a remote sensing analyst, you must be aware that if you are classifying a vegetation area, then a vegetation area reflects the most in NIR band. So when you are creating a false color composite with giving a red color to the NIR composite, you will realize the vegetation reflection, since it's highest in your NIR band, you will have the brightest DN values in the NIR band, and whatever these values are wherever, that will be selected as your vegetation area. Based on this method, you can classify the whole image, but this kind of method will require definitely a lot of work to do, and you must have an expertise in knowing what reflection represents what. So that is why there has been an invent in recent years regarding an digital image classification. In digital image classification, as the term suggests, it employs automated systems where a computer software can analyze the image based on your requirements. So that's an automatic situation. However, to have the best classification, you need an hybrid approach, because you never know the classified image as done by an automated system, the spectral signatures it undertook into consideration, how good enough they were for the information classes. So you need an hybrid approach where you utilize both the visual interpretation as well as your digital automated classification. That's in general the three approaches which can be utilized. Since digital image classification is a major classification technique, we will be discussing more about this technique and what are the various approaches which are applied in digital image classification. So, an approaches can be classified on the basis of the possibilities of type of learning. Now, what is type of learning? In type of learning, we have two approaches. One is your unsupervised classification and the other is your supervised classification. Now, what do I mean by these two approaches? In unsupervised classification, it's totally an automatic digital classification where the image is classified based on the clusters which the computer identifies itself. The user only has to give how many clusters it wants the system to identify. So that if you want only 4 classes to be identified, so the whole image might be classified and in 4 classes, and if there's no other class which no other or the spectral feature is different from the 4 classes, those pixels might remain unclassified. So that is the only extent to which a user works in an unsupervised classification. Whereas in supervised classification, an analyst gives some reference data or the training data set for the classification. Now, reference or the training data set is the data which you have collected for particular GPS locations, and you provide to the computer that okay, this position represents an urban area, this location represents a water body. So on the basis of that, automatic system finds out the spectral reflectances for those pixels, and on the basis of those pixels it classifies the images. Now these the basics of these analyzing the spectra of the training sites and classifying them in other various methods require statistical methods or the discriminant methods, which are like maybe a minimum distance, parallel piped or box classifier, or a spectral angle mapper, or maximum likelihood. So these are various techniques. Now I'll stop this discussion here on the unsupervised and supervised classification, because this has been discussed further in the next module, as these two techniques are the major classification techniques, and if you want to read about it more, you can go to our next module on this. Here I'll like to consider the other classification approaches. Now our second possibility of classification is based on how do we treat the spatial unit. Now what is a spatial unit? As I suggested first, that the spatial unit is your spatial resolution, that is your pixel cell size. Now based on the consideration of the pixel size, we can divide this classification into two types. One is your per pixel based, another is your object oriented classification. Now what happens in your per pixel classification? In per pixel classification, suppose this is again your raster here, and you have these values, equal cell sizes, and suppose you have certain value here, suppose 255, this is 0, 161, and whatever other pixels have the values here. Now what happens here when you are classifying this image on the basis of per pixel classification, we get another raster here which is also in the format of these pixels only. So what will it suggest? It will suggest whatever this digital number is representing, that will be represented here in the pixel. So this will be a water pixel, maybe, suppose, and this is 0, and maybe something it is representing in the NIR region. This is not vegetation, so we can say no vegetation here. So that is how we are classifying an image. Per pixel basis we know what that cell has been classified into. So there might be instances here where there may be some pixel which are misclassified, and suppose this was a river, but you will not know the direction or exact location of the river here. And why is that? Because there can be a misclassification like this, and you will not look at this, the river direction. So that is why it comes into play an object oriented classification here. So here you will notice that this is water and this is no vegetation. So in this case there is an issue that it might not clearly show the boundaries here, and there must be some misclassification also which may result in not showing you properly where the river is, because our spatial resolution is coarser. So what do I tend to tell by this? I will show you or explain you in the figure more about it. So if you will look in this image, you will notice first figure shows you the colors of the digital numbers, that is represented from white to black. The second is showing you the actual digital numbers. So what is happening based on these digital numbers or the spectral characteristics for the at least 3 bands, we classify an image like this. You will notice that this image is more higher resolution image here, but it still represents all these pixels, and these pixels are still in the format of pixels. You will notice that there are hard boundaries here. There is no mixing of it, and you can see that it does not classify an image in a manner that you can directly identify it as a water body or a water class, or maybe, and especially how much of the area is one agricultural plot. So that is why this kind of classification is also known as a hard classification, because the boundaries are very hard here and you cannot have any kind of fuzzy relationship here. That is one of the things. However, this classification is important when your surface is more homogeneous. So if you have an homogeneous surface, you can actually use this classification, but in reality the earth surface is not that homogeneous. So what actually one pixel is representing here might not be a true condition. Why do I say it might not be a true condition? As I suggested before, that 2 trees cannot be identified in a coarser resolution. So same here, in one of the pixels it could be a mixed pixel, that implies it might have an ending of an agricultural field and the road might be starting within that 30 meter itself. So if that happens, whatever is the dominant class, the reflection would be more towards that class, and that pixel will be classified belonging to that agricultural field only. So if that happens, you will know there is certain misclassification and you will assume that the whole pixel is representing agriculture. So to avoid that kind of classification, we usually go for object oriented classifications. Now, how is object oriented classification different from the pixel based classification? Basically, the first basic difference is, one is a hard classifier, the other is the soft classifier. As I suggested, the hard classifier, you have edges or the boundaries and they are very crisp boundaries. There is nothing which identifies a direction of the road or the direction of the water body. However, in the object based classification, you will find that it's more smoother application, and you will not find something like a salt and pepper classification, which is famously known for this pixel based classification. So when you are using an object oriented classification, it will cluster all the pixels which are representing water together, and it will form segments of that related pixels, and based on those segments the classification is done. So what is happening, as in your first case, this was your raster and these are your cells. So each pixel here was given a different class. It was analyzed separately based on your requirement. Now in object oriented classes, it's a fuzzy based relationship. What is fuzzy based relationship? That suppose this is a mixed pixel and your vegetation is supposed till here and the road is passing through here, or maybe this is a urban area here. Now the reflection of this, because the spatial resolution is coarse, so the reflectance or the spectral reflectance of this pixel would not be of a pure vegetation, and also it wouldn't be a pure reflection or the spectral curve of this urban area. So you will have a mixed pixel here. Now how does that happens in the object classification? In object classification, it will try to unmix this and provide a soft boundary, and if this is also your vegetation here, so your object will be considered from here to here. Unlike in the pixel classification where the vegetation would have been represented only in this pixel. So here you are getting soft boundaries and even this part can be included. That is why this is known as object based classification or a soft classifier. In the next image, you can see the difference of these both classifications. So you will notice that in object oriented classification, not only spectral content is important, also the tone, the colors, and even the location of the pixels is considered important. So as you can see in this image, these pixels, these white pixels are classified with this because this is a pixel based classification. So every pixel is treated separately and based on the reflectance or the spectral curve, that pixel has been conditioned to be with this class, and there is kind of a separate segregation of the pixels in this case. However, if you will notice here, these objects have been separated based on their location, tone, as well as how closely they associate with their neighborhoods. So you will find this location is a completely homogenized area and not segregated or heterogeneous as in this image. That is one of the reasons object oriented approach is considered more reliable and it's more into utilization nowadays. However, this pixel based classification has its own usage as it's more efficient and less time consuming as compared to this object based, where it has to provide neighborhood associations, it has to consider the clusters which are equivalent, and it takes a little more time to do this kind of analysis here. This object oriented classification has one more major difference as compared to the pixel based classification, and it's highly important to understand this difference. As you notice, in a pixel based classification we consider at most 3 or maybe 4 bands but of the same satellite data. That is, if you are using a Landsat 7 data, then all the bands are of Landsat 7 data only. You do not mix and match the satellite data bands and the sensor information here. However, in object oriented classification, since you are classifying the image on the basis of objects and there is a neighborhood relationship involved, you can even use with the satellite data the shape files available for the area and even the digital elevation model. Thus, in an object based model, the spatial resolution is not that important and you can have different spatial resolution data with you and you can still have a classification obtained. So in this manner, the object classification is much better as compared to your pixel based classification. Thirdly, when you look at the data and you say, okay, we have a high resolution data available to us, we will use a data which has a 1 meter resolution. So of course that data is good, but if you automatically classify that image, there are chances of having more spectral variability as compared to a coarser resolution data, because everything gets stored when you have a very high resolution data. So there are chances of misclassification a lot if you are using a pixel based classification. However, in object oriented classification, it will try to group together the spectral variability also into one group based on the location of that area, and you will have a much clearer version when you are using the object instead of the pixel based. So these are your two methods or approaches based on your spatial unit. The third and the last approach is based on the data distribution, or what assumptions do we take about the data that is being used to classify our images. Based on that, we have two techniques here. One is non-parametric and other is parametric. Now, based on the data assumptions, we have parametric classification. What do we imply by parametric classification? We imply that in parametric estimation or approach, the data distribution is already considered. What do I mean by data distribution? It means, suppose we have a training set. We assume that the data is normally distributed, and that is your basic pre-classified model which we use in this system, and based on that system the image is classified. So for an example, if we have a maximum likelihood system, in a maximum likelihood system we have a curve or a maximum curve which shows us what is the mean value for that particular class, and since we have collected the training data set, based on that we will know what is the standard deviation or what is the limit that a particular pixel is allowed to go, and if it falls within that spectral unit or spectral curve, this pixel would be classified into that class. So what I said can be shown here. Suppose here, now if you have a training set, you go on your field and suppose you collect the data at certain locations, and suppose these locations are equivalent to 50 observations, and these 50 observations are supposed belonging to only one class. Now if you have 50 data of one class, can you represent this on a graph? Of course you can represent, and you will get something, a curve like your bell-shaped curve or a normal distributed curve. So here this value represents your mean value for this class in the spectral space, and here approximately you are getting your standard deviation between +3 and here -3. So this is your normally distributed curve here. Now if you classify this unknown pixel, if the value in the feature space of this pixel falls within this curve location, then you say this pixel also belongs to the pixel in this class. Otherwise, whichever graph is represented by which other class, this pixel will fall into that category. So the classification of this pixel is actually determined with the normal distribution curves of all the classes which we want to classify the image into. So this is also kind of a hard classifier. So if we don't want to use this, we go for non-parametric options. The non-parametric options, as the name suggests, it doesn't assume any data distribution for the training set which we have. So in non-parametric, there can be many other approaches, but currently we will talk about two approaches, which is NNN and SVM. NNN, as you know, is an artificial neural networking, and SVM is another technique, that is your support vector machine technique. Now what happens in ANN? ANN actually works like your neuron system. So what happens in your neuron system? Suppose something pricks you for the first time, you do not know whether it will hurt you or not. So your response time is a little late. However, if you are pricked a second time at the same location with the same thing, your brain automatically knows that if that needle pricks you, you will feel the pain. So your response time changes with that. Similar technique is used in classifying an image here. So it's an artificial neural networking, where based on previous classifications and new permutation and combinations, it provides a new learning, and based on this new learning, the image is classified. So there's no predefined mean, variance or the standard deviation taken into consideration. It provides new learning to the classification and you get a classified image. Second important thing is your support vector machine. Now what happens in support vector machine? So in support vector machine, I'll show you with two band datas on a spectral plot or on a scatter plot. So here X represents one of the band data and Y represents the other, and this is your feature space. Now these stars and circles are representing two separate classes. As I have been saying time and again that the clusters represent different classes. So here you can notice that there are two separate classes. Now what does an SVM do? SVM provides you a optimal hyperplane within these, which separates these two classes on the basis of a distinct boundary. Now you will notice we have three lines drawn here. So what is it showing? That the optimal hyperplane is represented by B. Now why is B an optimal hyperplane? It's an optimal hyperplane because it's creating a extreme distinction between these two classes. On base of this hyperplane, it creates a classification of the image. So you have this classification would involve two separate classes, and these are known as the support vectors. Therefore, the name as support vector machine. Now, if you will look at the second figure, you will say that all these three are optimal hyperplane. But how would you know that which is the best out of these three? The best would be the C. Now, why is C better? Because you will notice that there is a distance between all the points here from C, as well as C also has the maximum distance from all the points here. So C is representing an optimal hyperplane here, as it has maximum distance from both the classes. If B would have been taken, then it's exactly on the margin for this kind of class, and A is on the margin of this class. So it won't justify when you classify the whole image. That is why the optimal hyperplane is C in this case. Now this classification has gained a lot of importance in recent times, and it also includes a penalty parameter that allows a certain degree of misclassification. Now as I talked about the penalty, what happens, like suppose this is your one class represented by these crosses, and there is another class represented by circle, and this goes your optimal hyperplane. However, there can be a situation that certain pixels are misidentified here. So for these kind of pixels, we have two options. One is outliers. So this can be automatically removed while we are doing using this support vector machine. Another is, suppose you have a pixel somewhere here, or maybe 2-3 pixels which follow out here. So we have an option of a penalty where we have these consideration under penalty classification, and these pixels are sure to be classified. So we can provide a scale option where these pixels are taken into consideration. So this is the major techniques for the non-parametric estimation. There are also other techniques which are available for classification, but these which have been discussed here are the important ones. Now we will talk about the limitations and the advantages of digital image classification. Now the advantages of these image classification are that because it's a digital image classification, you can easily classify a global map also, and you might not be concentrated only a small area or region for classification. Plus, if you have the classification, because the satellite data is available on regular intervals, you can notice the changes in the land use, land cover for different scenarios and different regions, and even in temporal analysis. How we can do the change detection, we will be discussing it in the next module. For now, that is one of the important advantage of having the classification and using digital image classification. However, there are certain limitations of doing a digital image classification. So what are these? First of all, they are rarely perfect. Why? As I said, you will notice there are mixed pixels, and sometimes dominant spectral characteristics of one are not able to be identified. So you might have some misclassifications. Even after misclassifications, you are able to get a general idea of the area, what actually a land cover is present there, what kind of information you are getting from that satellite data. How can this be important advantageous is because you can still use it for maybe delineating flood prone zone maps. If it's a floodplain zone and if it's highly vulnerable, you can realize how to have mitigation measures taken place there. So that is your one advantage of digital image, even though it's at a coarser resolution and it might not be that accurate. Secondly, with the satellite data, it is also important to notice that you need to have it atmospherically corrected images. Otherwise, the same image can have different spectral characteristics. What do I mean by that is, suppose you have a December image with a lot of cloud effect. So unless you remove the cloud effect, the pixel can be misidentified or misclassified. So before going for the classification, these images should be properly rectified and they should be also georeferenced properly, so you know where the spatial object or which pixel is representing the actual ground surface. Then only the classification will work. That is for now. So to summarize, in the end, it is suggested that the semi-automated approach is the best approach for classification. That is, it involves digital automatic classification along with visual interpretation editing, so that you can have the best possible classified image. Once you have a classified image, you undergo an accuracy assessment of the classified image. This is again a separate topic of accuracy assessment, which will be taken in another module and is not combined here. So once you have done this classification, it's on the basis of this classification you have to decide which approach is the best and what method is easily available for you and how the regional location is. If it's an homogeneous system, you can have pixel based classification. If it's a very heterogeneous image, then you might go for object oriented. If it's a higher resolution image, again object oriented. So on the basis of the regional application, on the basis of the satellite data available to you, you can decide which classification technique you want to use. For further reading, the books have been already provided in the e-text and you can read any of those texts, and I think that would be more than sufficient for you to understand the classification techniques. Thank you.